So hi everyone, I'm Damiano Azzolini from University of Ferrara, and I will present our work as semantics for hybrid probabilistic logic programs with function symbol, joint work with Fabrizio Riguzzi and Evelina Lamma. So we introduce a new semantics for hybrid probabilistic logic programs with function symbols. We prove the semantics well defined, so it assigns a probability value to all queries for programs with a two-valued well-founded model. In the third bullet point, you can see a reference to the paper. So in general, logic is useful to model domains with a complex relationship among entities. There are several forms of logic. We have first-order logic, logic programming, and description logic. We focus on logic programming, and it has some interesting features such as closed word assumption and Turing completeness. Among all the languages, Prolog is the most famous one. However, logic does not handle well uncertainty, and in this case, we need to resort to probabilistic logic programming. So in general, a probabilistic logic program following the distribution semantics defines a probability distribution over normal logic problem. Here you can see a really simple example that models a game with three cards. So we have ace of spades, ace of clubs, and ace of hearts. In the first two lines, we have two probabilistic facts, spades and clubs, and spades is true with probability 1/3, and clubs is true with probability 1/2. Then we have three clauses, so pick 0 spades is true if spades is true, and similarly for the other two. We can compute, for example, the probability of the query pick 0 hearts by multiplying 1 minus 1/3 times 1 minus 1/2, and we obtain 0.33. However, when a program contains variables, function symbols, and at least one constant, its grounding is infinite. So suppose we extend the previous game, and now consider more than one round. And the game stops when the player picks the ace of hearts. So we add three more clauses for pick. And for example, at line 2, we have pick SI spades if pick I hearts is false and spades SI is true. Here, the function symbol is S, and S denotes the index of the round. So the first round has index 0, the second round has index S0, the third round SS0, and so on. We can be interested, for example, in computing the probability that the player pick at least once spades. So the line 8, close at line 8. However, some programs may also have continuous random variables. So for example, in the first line, the variable x follows a Gaussian distribution with mean 0 and variance 1. Then if we query A, the probability of A is given by that the probability of x being greater than 3. But what happens when we use both continuous, discrete random variables and function symbols? So again, let's extend the previous program, and we add another requirement. So the player also spins a wheel, and the game continues only if the axis is in the range pi to pi. So we add a continuous probabilistic fact. In this case, line 2, the variable x follows a uniform density between 0 and 6.28 to approximate to pi. And then we modify all the 6 clauses for pick. Here I've reported only 2 clauses. And we add for pick 0 spades, for example, and angle 0v, v greater than 3.14. And similarly for all the other 6 clauses. Still, we are interested in the probability that the player picks at least once spades. So how can we compute the probability of this query? We have a countable set of continuous random variables, and all these continuous random variables are identified by 0, S of 0, and so on. And each element has a range 0 to pi. We have also a countable set of discrete random variables, and to perform inference or compute the probability of a query, we can consider mutually disjoint covariant set of walls. So omega. And the set omega is the union of all the subset omega 0, omega 1, and for example, omega 0 has the following structure. So focusing on the second line of omega 0, we have x0 in pi to pi, so the wheel at round 0 was in the range pi to pi, and then we have y0s equal to 1. So at round 0, spades was selected. For omega 1, we have x0 pi to pi. So at round 0, the axis was in the range pi to pi. Y0s this time is 0, so we do not select spades, but Y0C is equal to 1, so we select clubs. And then we move on to the second round, so down round indexed by 1. So x1 is in the range pi to pi, and y1s is equal to 1. And similarly for the other omega. Overall, we can compute, for example, the probability of omega 0, and in general for the other omega I, by considering the contribution of the discrete and the continuous variables. In this case, we have 1/3, which is the contribution of the discrete random variable space, and 1/2 pi, which is the contribution of the continuous one, the angle. In the limit, we get as probability for the query at least one space 1/5. So overall, we consider separated the set of discrete and continuous random variables. The probability space is the product of the probability spaces generated by the two sets, continuous and discrete random variable. And we prove that the semantics assigns a probability to all queries for a large class of programs. And we do this proof through the definition of a series of operators, and we prove that those operators are sound and complete. So to conclude, hybrid probabilistic logic programs have a huge expressive power, and if we add the function symbols, we can increase the possible queries. And in this work, we propose a new semantics for this type of programs, and we prove that this semantics is well-defined. As future work, we plan to develop also inference algorithm for hybrid probabilistic logic program with function symbols. And this concludes my talks.